Welcome back. So here in this particular video, we're going to be talking about section 3.11, spectroscopy and the electromagnetic spectrum. We want to just touch on the high points here as you finish your review for this. But remember here, when we're dealing with spectroscopy is going to be looking at a way of using light to understand the structure of the matter that you're looking at. And since we're dealing with light, we got to make sure that remember that light here can be understood in terms of various properties of light. We know that it's quantized, so it's going to be in packet formats, but that also means that we can actually treat it with discrete ways by looking at its frequency. So we can look at frequency, which is going to be represented by a letter F, or it can be represented by this symbol here, looks like a Greek V. We can also look at the wavelength of the wave, and that symbol is that. And so the wave here, just to distinguish the parts, we can look at the wave as a sine wave, like so. And if we're going from the top of one of the waves to the top of the other, the distance between here, this here is known as the wavelength. And the idea is that if we can look at the wavelength, we can determine the relationship between the wavelength and the frequency of the wave by looking at a couple of equations. And so those equations here are going to be the following. And so let's go ahead and get these equations up here on the screen. I'm going to go ahead and move things aside a little bit. And so put this over here, and what we've got here are the following. So we know that the speed of light is going to be equal to the wavelength of the wave multiplied by the frequency. Another equation that we need to be very aware of is going to be the energy equation of a wave. And that is, if we take Planck's constant, which is represented by the letter H, that's the variable, and we'll multiply that by frequency. The combining, or the variable that exists in both of these equations that can be used to unite them is the unit of frequency. So if we write both of these equations for frequency, we can come up with a third equation that is presented to us. And that would be that the energy of a wave is going to be equal to the speed of light times the Planck's constant divided by the wavelength. And so it'll be these three equations here, the speed of light equation, the energy equation, in this format with frequency, or in this other format with wavelength, that then you can use to understand the concepts here in this section. We do also know that there are a couple of items that you need to be aware of, and that is the electromagnetic spectrum. So let me bring in a copy of the electromagnetic spectrum for us to take a look at. So here is a copy of the electromagnetic spectrum. Let me go ahead and zoom in a little bit more on this thing here. And so we can see that in the spectrum here, we're going to have a couple of items that we need to be aware of. That is that we've got a broad range of types of wave. On the left-hand side, we've got X-rays, and on the right side, we've got long waves. And so this particular spectrum is designed or drawn out so that you've got the reds on the right-hand side and the blues, indigo on the left, corresponding to Roy G. Biv, but not in that order. It goes actually from right to left in this particular case. The main thing to notice here is the trend that we see with frequency, which is identified over here along the top, and then wavelength along the bottom. The general trend that we see here is as frequency increases, and you see that the increase is happening as you go from right to left, the number's getting bigger as you move to the left-hand side. As you do that, the corresponding wavelength is getting progressively smaller. And so that brings us to a very good, important point with this, is that the wave here, the pattern that we're going to look at is that when we look at the frequency, we're going to see that the frequency of a wave, as this goes up, that's going to correspond to a increase in energy, and it's also going to correspond to a decrease, however, of the wavelength. So this is a very important pattern sequence to be aware of. So go ahead and just remember that. Now, there are 4 regions in this area that you need to be aware of, and the effect. And so let's take a look at these now. And so the 4 regions that we need to be fully aware of are going to be the regions of the ultraviolet, the visible light spectrum, which includes the entire visible spectrum, Roy G. Biv, the infrared spectrum, region and the microwave region. And so if we look at these a little bit closer, what we've got here is in the ultraviolet, you're going to see, let me zoom in a little bit more here. We can see that in the ultraviolet section, you are going to end up getting some information that is going to be related to the valence electrons. Same thing for the visible. So these two regions are going to give us information about the structure of the molecule or the compound that we're looking at, but we're going to be looking and investigating at valence electrons in order to get that understanding. In the infrared region, we're going to be looking at vibrations that occur within the molecule, and then finally in the microwave region, we're going to be looking at molecular rotations, things that are going to be affecting the polarity or how the orientation of the molecule. And that usually gives us information about spin, but in a shortened way, that is talking specifically about polarity of that particular molecule. So let's go ahead and summarize all of these things down together and get an idea of what we're going to do with that. And so let's see here. Let me see if I can group a couple of these items and move them out of the way. All right, so if we come in here and we zoom in a little bit here, let's break this down based on the regions that we're looking at. Okay, so here the regions are going to be UV for ultraviolet. Ultraviolet is going to be the highest energy. We already saw that here on the spectrum that I showed you. This is going to have the highest energy of the four regions we're looking at. And of the four regions, what's going to be known or learned from this is the UV light's going to allow us to understand electrons as they are excited. So electron excitation. And so we can use this to understand the structure of an atom. We can look at the shifting of energy levels of an electron from one level to another level, from ground state, for example, to excited state. And that allows us then to kind of put things together so we can actually see what the spectral line is, or that signature that you're going to get from a particular atom who's undergoing those excitation events, or what we call transition events. So when we have this electron excitation, these are actually called transitions. And you're able to kind of put those together, and you can get a better idea of the shifting that happens in an atom, and that can help you identify perhaps the number of electrons that are in there, so you can get a configuration of sorts for the matter that you're studying. But it's usually just because of the high energy of the ultraviolet light, you're going to get a lot of this shifting of electrons from one orbital to a higher orbital. Now, the other region that we were also looking at here was the infrared region. So this is known as the IR region. This is a little bit lower in energy than the ultraviolet. And what's going to happen here is there's not enough energy for this particular wave to impact electrons to get them to go through a transition state from one ground state to a higher level. So instead what happens here is that these particular types of energies, since they're lower, what usually happens here is you're going to end up getting vibrations in the molecule. And that's going to lead us to, or allow us to look at and understand a little bit more about the types of bonds that are in there. So this informs our understanding of the bonds. And so in particular, the bond, we're going to be looking at the bond type. That's going to be, it can be inferenced, and also the bond order. So you should be able to tell if you've got a single, double, or triple bond, and by extension, whether that is a big, lengthy bond or a shorter bond, and that kind of goes synonymous with the bond order that you've got in terms of first, second, or triple, first, single, double, or triple bonds that you've got here. Okay, so remember here that the single bonds here are going to be the longest, and the triple bonds, these are going to be the shortest. And clearly here the double bonds are going to be right in the middle. So we'll just call them middle length type of bonds. But this is the kind of information that you're going to get from the infrared region through an IR spectroscopy or an infrared spectroscopy. You'll also learn about the types of functional groups that are going to be inside the compound, because they're going to have vibrations at very specific frequencies. They'll begin their vibration effect at that region, which in turn is going to allow us to understand what kind of specific groups are going to be found within the compounds that you're studying. So depending on the amount of light frequency that you're being able to shine on the molecules or that particular sample, it's going to be absorbed by those molecule components, and that will allow it then to, once it's absorbed, then those frequencies then are going to be represented in the graph that you're generated, which will then inform your ability to identify various functional groups within the compound. Now the last component here that we're going to look at is going to be the microwave. Now the microwave component here, this is going to be the lowest energy of the 4 regions we looked at. And so what we got here with this particular region here, since there's very low amount of energy associated with this type of wave, typically what we're going to learn more from the microwave region is going to be, it's going to give us information about the molecular rotation of a sample, but the sample does have to be in the gas phase, however. That's one of the things, the limitations about this. So, but when you do actually use this technique and you bombard the sample with microwave energy, that does allow us then to look at the energies that are involved in transitions that are rotational in nature for those molecules. That allows us then to understand the interaction that's going to be occurring between the sample, the molecules, and the electromagnetic field that's going to be formed around it, so that the molecule is going to arrange itself according to how it responds to that EM field. And so this is what kind of gives us and informs our ability to understand the polarity. And so that all of this here is going to help us understand the polarity or the overall molecular rotation of that particular molecule. And so we'll just say here molecular rotation. Okay. And so those are the items that you need to know in terms of 3.11. There's the main idea here is that you want to make sure that you look at the energies. Can you calculate frequency, energy, wavelength? Can you understand the different nuances of the 4 different regions? Keep in mind that there's 4, UV. Also here in this section, I didn't write it down, but remember here there's also visible. The visible light is just a little bit lower in energy, but it's also going to cause transition shifts of the electrons from one orbital to the other as it absorbs that light. So be familiar with the concept of how energy is absorbed, what it means to be excited, to have an electron that goes from the ground state to the excited state, and then just understand that different types of regions in the electromagnetic spectrum are going to be used for various different types of analyses on the compound structure. The higher energies can be used to understand the transitions of electrons. And then as you move down lower in energy like IR, then because it's lower, then you can only understand the vibrational things. So IR is usually used to identify the bonds, information about the bonds and structure, and maybe some functional groups that might be present. And then lastly, the microwaves are going to be used to identify how that molecule is actually aligned in space according to how it responds to an electromagnetic field that might be induced by that wave. Okay, so those are the topics of 3.11. Continue your review, and we'll see you soon.